In the last lecture, we were looking at dimensional analysis for heat transfer in a heat exchanger. Consists of a tube side and a shell side. You have hot fluid entering on the inlet at the tube side and gets cooled by contact across the pipe wall with the fluid on the shell side, and therefore it cools down. And we were considering a simplified situation where we were just considering the heat transfer from the fluid to the wall of the pipe, such that the average temperature difference between the shell side and the tube side was delta T. And we wanted to find out the relation between the dependent and the independent quantities. I had said that the dependent quantity in this case is the average flux. The flux per unit surface area of the tube across which the heat transfer takes place. Okay, so, that is the dependent quantity. Independent quantities, geometric quantities, length and diameter of the pipe, flow quantities, the flow velocity and the fluid properties, density and viscosity, thermal quantities, the temperature difference that is driving the heat transfer, the thermal conductivity and the specific heat. And we had written down the dimensions of all of these quantities. There was 1 dependent and 8 independent quantities, 1 independent and 8 dependent quantities, and 4 dimensions: mass, length, time and temperature, which means that 1 dependent and 4 independent dimensionless groups. Now, we had made a simplification here, and that is to say that there is no interconversion between thermal energy and heat energy, thermal energy and mechanical energy, and that is that thermal energy can be considered as a separate dimension H, which is different from mechanical energy, which is mL square T power minus 2. The thermal quantities were expressed in terms of the thermal energy, the average heat flux, the specific heat, the thermal conductivity and the temperature difference. Okay. So, the average heat flux is the energy per unit area per unit time, which is H L power minus 2 T power minus 2. And then we had the specific heat, which came from the relation that the change in enthalpy is mass specific heat times the temperature difference. And so, we got H m inverse theta inverse. And also for the thermal conductivity here, we had got the dimension as H L inverse T inverse theta inverse. Okay. Now, we have 5 dimensions and therefore, only 4 dimensionless groups, of which one is dependent and the other is independent. Dependent dimensionless group is the non-dimensional average flux, the Nusselt number, scaled by quantity which has the same dimension as the right side of Fick's law of diffusion, that is QAV by K delta T by D. Okay, so, this is the dimensionless flux. Independent dimensionless quantities L by D, the Reynolds number, and another number which has the specific heat, the thermal conductivity and either the density or the viscosity. Specific heat and thermal conductivity, you can cancel out the heat dimension, and then you need something to cancel out the mass dimension in specific heat. Okay, that was either the viscosity or the density. If you use the viscosity, then you get this dimensionless group Cp mu by K, called the Prandtl number, which we will see later is the ratio of momentum diffusion and thermal diffusion. Alternatively, you could write this as what is called a Peclet number, which is a ratio of convection and diffusion, rho V average d Cp by K. So, therefore, the Nusselt number is a function of the Reynolds number, the Peclet number and L by D. Okay, so, that is the relation between the dimensionless groups. Okay. So, the major assumption that we had made here was that there is no interconversion between thermal energy and mechanical energy. There are situations where there could be interconversion. For example, as the fluid is flowing, there is fluid friction which generates heat. Okay, you know that if you rub two surfaces relative to each other with a fluid in between, the fluid there gets heated. The reason is because the relative motion of fluid layers relative to each other results in viscous friction which generates heat energy. Okay, so there could be an interconversion between thermal energy and the mechanical energy if the mechanical energy generated due to fluid friction is a significant fraction of the thermal energy transport. Okay, so in that case you could have an interconversion. So how do we determine the dimensionless group that determines this interconversion between thermal and mechanical energy? Okay. This dimensionless group is actually called the Brinkman number. Okay. And this is the ratio of the energy dissipation rate due to viscous friction and the energy transport rate due to thermal conduction. Rather than writing it as the ratio of rates of energy transport and energy generation dissipation due to viscous friction, we can write it as the ratio of a rate of energy transported per unit length, okay, due to fluid friction, and the rate of energy transported per unit length of the pipe due to thermal conduction. Okay. So, the rate of energy transport per unit length, it will have dimensions of energy, okay, m L square t power minus 2 per unit length per unit time. Okay. So, this is a rate of energy transport. Okay. Rate of energy transport is an energy transport per unit length per unit time. Okay. So, let me just make that clear. Is equal to m L square t power minus 2 by L t, okay, is equal to m L t power minus 3. Okay. So, now we have to calculate what is the rate of energy transport due to viscous friction, rate of energy transport due to thermal conduction. Okay. Rate of energy transport due to thermal conduction Okay. This has to depend upon the temperature difference and the thermal conductivity. Okay. This is a rate of energy transport. So, it has depend upon the thermal conductivity and the temperature difference, and maybe the diameter to some power alpha. Okay. And if I express this in terms of dimension, the rate of energy transport due to thermal conduction m L t power minus 3. The thermal conductivity has dimensions of m L t power minus 3 theta inverse. Okay. This is the thermal conduction. Okay. Into theta into L power alpha. Okay. And you can easily see from this that alpha is equal to 0. Okay. So, therefore, the rate of energy transport per length per time due to conduction, okay, is proportional to k times delta t, where k is the thermal conductivity and delta t is the difference. Note also that the flux was equal to k delta t divided by length. Flux is transport per unit area per unit time. So, transport per unit length per unit time is just k delta t. Viscous dissipation rate per unit length per unit time. the viscous dissipation rate per unit length per unit time. It has to be equal to mu times V average. It has to depend on viscosity because it is viscous friction that is resulting in dissipation of energy. It has to depend on the average velocity, okay, because the average velocity is the greater the flow velocity, the greater will be the dissipation, and it can also depend upon the length scale. So, how do we calculate this? The left side dissipation per unit length per unit time is m L T power minus 3 is equal to viscosity is m L inverse T inverse into L square T inverse power alpha and L power beta. And from this you can easily verify that alpha is equal to 2 and beta is equal to 0, okay, just simple analysis. Therefore, this is equal to mu V average square, which means that the dimensionless Brinkman number ratio of viscous dissipation to thermal conduction, ratio of viscous dissipation of energy per unit length of the pipe per unit time divided by thermal conduction per unit length of the pipe per unit time is just equal to mu V average square by K delta T. Interestingly, this does not depend upon the diameter at all. Okay. Interestingly, this does not depend upon the diameter at all. Okay. When this Brinkman number is small, the viscous dissipation is much smaller than thermal conduction. So, we can assume that mechanical and heat energy are different dimensions because there is no interconversion between mechanical and thermal energy. When the Brinkman number is comparable to 1, okay, when it is significant, it is not small, then there is interconversion, and the Nusselt number in that case will depend upon the Brinkman number as well, okay, in addition to the other Reynolds and Prandtl numbers and the length ratio. The Nusselt number will depend upon the Brinkman number as well, and it has to be included in the correlation. In most normal situations, this is actually small. Okay, so, the Brinkman number does not enter into the calculation. Okay. So, this is a rationale for why we had considered thermal energy and mechanical energy as two different quantities. Okay. Okay. Let me show another example of how we can use dimensional analysis in order to simplify a problem. Okay. So, this problem, okay, so I do let us say a pilot project in order to find out how long it takes for a particle, a wet particle, a saturated particle to dry in a fluid given a certain temperature difference between a certain temperature difference between the particle and the fluid. Okay. So, I have a particle of diameter 1 millimeters, okay, and this particle is at a temperature of 40 degrees centigrade, okay, on the surface, and the ambient temperature is 10 degrees centigrade. Okay. So, rather than drying, I am talking about cooling of a particle in a fluid. Okay. So, I put in a particle of I put in a particle at a temperature of 40 degrees centigrade into a fluid which is at a temperature of 0 degrees centigrade, and then examine the temperature of the particle as a function of time. Okay. And it takes 60 seconds for the particle temperature to decrease from 40 degrees centigrade to 10 degrees centigrade. Okay, that is what is given. Okay. Now, instead of 1 millimeter, if take a larger particle of diameter 2 millimeters, exact same composition, same temperature, initial temperature 40 degrees centigrade, in ambient 0 degrees centigrade, how long will it take for this particle temperature to decrease to 10 degrees centigrade? Okay, that is the question. This is often encountered in things like scale up, for example. Okay, when you want to go from a smaller system to a larger system, you have a model system which is a smaller one, and you do experiments on that, and then you have to predict what happens for the larger system. Okay. And additionally, the rate of cooling is determined only by the conduction of heat in the fluid, and not by by the transport of heat in the fluid, and we will assume that the fluid is stationary. So, the velocity is not important. Okay. So, what does the time required for cooling depend upon? Okay. Time for cooling. Okay, depends on diameter d, okay, temperature difference delta T, okay, and then the properties of the particle, okay, that is the density rho, the properties of the fluid, okay, density rho, thermal conductivity K, okay, and the specific heat. Now, in these two situations, the temperature difference is kept exactly the same. The temperature difference at the initial stage and the temperature difference at the final stage is kept exactly the same. Okay. So, therefore, one has to find out what is the time required for a particle of a higher diameter as compared to a particle of a lower diameter. Okay. So, therefore, I have the dimensional parameters, the time t with dimension t, that is what I want to find out, that is the dependent dimensionless group. The independent dimensionless group are the diameter d with dimension L, density rho m L power minus 3, viscosity, the specific heat. Okay. There is no flow here, so I just have the specific heat. Okay. Conductivity K with dimension m L T power minus 3 theta inverse, okay, and specific heat with dimension L square T inverse T power minus 2, inverse. Okay. So, these are the quantities. There are a total of 5 quantities, 4 dimensions, mass, length, time and temperature, only one dimensionless group, and that dimensionless group you can get by the usual analysis. That dimensionless group turns out to be is equal to T k by rho C p d square. Okay. So, therefore, this has to be a constant. Okay. T k by rho C p d square has to be a constant for this cooling process. What that implies is that the time for cooling is proportional to the diameter square. The time for cooling is proportional to diameter square. This we got just based upon dimensional analysis. For a particle of diameter 1 millimeter, if it takes 60 seconds, for a particle of diameter 2 millimeters, it should take 60 times d square, that is 4. So, it should take 240 seconds for cooling this particle of diameter 2 millimeters. Okay. Provided the initial temperature difference and the final temperature difference are both kept a constant. Okay. So, this illustrates the use of dimensional analysis in order to find out what is the time required for cooling a particle. Okay. Finally, let me conclude this section with the discussion of the pressure difference. For fluid flow. In our discussion of heat transfer across a heat exchanger, we had expressed it in terms of the average heat flux, that is the heat flux per unit area, per unit surface area of the tube. That heat flux you would think would increase as the surface area increases. So, as you kept increasing the length, you would think that the total heat transfer rate keeps increasing. That is true. As the length increases, the whole total heat transfer rate does go on increasing. However, in order to pump the fluid through this tube, you also have to apply a pressure difference across the inlet and outlet of the tube. Okay. That pressure difference, the energy cost for applying that pressure difference also increases as you increase the length of the tube. So, it is of interest to find out what is the pressure required in order to pump the fluid at a given velocity across some particular length of the tube. Okay. There is a trade off here. Okay. You would think that if you keep increasing the length, you would get more and more heat transferred, but there is a cost because the pressure difference also goes up, and you have to know what is the pressure difference in order to determine what is the optimum length of the tube for which you get a maximum amount of heat transfer at not too excessive pumping cost. So, the pressure difference across a fluid across a pipe for a fluid flow. Okay. So, I have a fluid which is flowing through a pipe of diameter d, okay, across which I have applied a pressure difference delta P. And let us assume that the length of this pipe is L. Okay. Now, why is this pressure applied? That is because there is a force acting on the surface of the tube, a wall shear stress. If you want to flow fluid across a surface, there is a stress exerted, okay, on the wall. Okay. That stress is exerted in the downstream direction on the pipe, and the pipe in turn exerts an equal and opposite force in the upstream direction on the fluid. Okay. The force exerted on the fluid is in the upstream direction. Okay. The stress that is exerted by the fluid on the pipe is in the downstream direction. Okay. As it is flowing, the fluid exerts a stress in the downstream direction, and there is an equal and opposite force exerted in the upstream direction on the fluid. Okay. The relation between the pressure difference and the stress is basically a force balance. Okay. The force in the downstream direction between the inlet and the outlet due to the pressure difference is equal to the pressure difference times the cross sectional area. For a pipe of diameter d, it is pi d square by 4. Okay. This is the force being exerted on the fluid in the downstream direction by the pressure difference across the two ends. That is, due to the pressure difference across the two ends, there is a net force that is exerted on the fluid. That is equal to the pressure times the cross sectional area. And there is an equal and opposite force acting on the fluid in the upstream direction due to the wall shear stress, the stress at the wall. That is equal to the wall shear stress. Okay. This is acting in the negative direction. Okay. So, it is equal to minus tau w into pi d L. Okay. Surface area of the pipe is pi times d times L. Pi d is the perimeter and L is the length. So, this straight away gives a relation between the wall shear stress and the pressure difference. Tau w is equal to minus delta P by L, okay, into d by 4. Okay. Minus delta B by L into d by 4 is the relation between the wall shear stress and the pressure difference. Alternatively, you can write minus delta P by L is equal to 4 tau W by D. Okay. So, this is the force exerted per unit length of the pipe. Okay. So, as the pipe length increases, you have to exert more and more force proportional to the more and more pressure difference proportional to the length for getting the same velocity. Now, how do we determine this from dimensional analysis? Okay. From dimensional analysis, okay, the dimensional quantities, the dependent quantity, what we want to calculate is the pressure difference or the wall shear stress, because the wall shear stress and the pressure difference are related by a force balance. Okay. I will just take the wall shear stress as the dependent quantity. This has dimensions of m L inverse T power minus 2. Force per unit area, okay, force is m L T power minus 2, force per unit area is m L inverse T power minus 2. Okay. And the independent quantities are the diameter d with dimension L, the flow velocity V average with dimension L T inverse, and the fluid viscosity and density rho with m L power minus 3 and mu m L inverse T inverse. So, I have one dependent and 4 independent quantities, 3 dimensions, therefore, I will have one dependent and one independent dimensionless group. Okay. The independent dimensionless group contains rho, V, D and mu, and that is of course the Reynolds number. The dependent quantity is the wall shear stress scaled by something. Okay. And you can either scale it by the viscous scales or you can scale it by the inertial scales. Okay. The wall shear stress can be scaled either by the viscous scales or by the inertial scales. What is conventionally done is to scale the wall shear stress by the inertial scale. Okay. Stress is force per unit area. Okay. Stress is force per unit area. Force per unit area has the same dimension as energy per unit volume, because energy is equal to a force times length. Okay. So, force per unit area has the same dimension as energy per unit volume. Okay. So, you can scale the wall shear stress by something that has same dimension as energy per unit volume. Kinetic energy per unit volume is mass per unit volume times half V square. So, therefore, if I take half rho V average square, okay, this is a dimensionless group. Okay. So, that is the dependent dimensionless group, okay, also referred to as the friction factor. Okay. Therefore, the relationship between the independent and the dependent dimensionless group is friction factor is equal to some function of the Reynolds number, where friction factor is the wall shear stress divided by half rho V average square. Okay. Using this relation between tau w and V average, I can also write this as minus delta p by L into 1 by 2 rho V average square. Sorry, I should have a d there. Okay, half rho V average square in the denominator and dividing this by multiplying this by d by 4 here. Okay. Multiplying tau w by d by 4 and I will get minus delta b by L into d by 2 rho V average square. Okay. So, this is what is called the friction factor. Okay. Once again, you can think of limiting situations. Okay. When the Reynolds number is small, then inertia should not be a factor. Okay. When the Reynolds number is small, then inertia should not be a factor. Okay. And what that means is that, okay, the wall shear stress by mu V average times, okay, when inertia is not a parameter, you can get only one dependent dimensionless group. There is no independent dimensionless group because density inertia is neglected. So, density is 0. Okay. There is only one dependent dimensionless group, which is tau w by mu average V average by d. Okay. This has to be a constant. Okay. So, this has to be a constant in the limit of low Reynolds number where inertia is not important. Okay. In that case, the friction factor is equal to a constant into mu V average by d by half rho V average square. Okay. This is equal to some constant into 2 mu by rho V average d, and this is proportional to 1 over the Reynolds number, because Reynolds number is rho V average d by mu. Okay. So, in the limit of low Reynolds number, the friction factor has to be inversely proportional to the Reynolds number, because the friction factor was scaled by the inertial scale. Okay. So, the friction factor has to be inversely proportional to the Reynolds number. In the limit of high Reynolds number, inertial effects are dominant. However, in the limit of high Reynolds number, there is something called transition to a turbulent flow. That is something we will discuss later in this course. Okay. When there is a transition to a turbulent flow, then the friction factor has a more complicated dependence on the Reynolds number. Okay. When there is a transition to a turbulent flow, the friction factor has a more complicated dependence on the Reynolds number. So, this completes our dimensional analysis. We examined mass transfer from a particle, heat transfer in a shell and tube heat exchanger, and we also examined the pressure difference for pumping fluid in a pipe of a specific diameter, the friction factor, the dimensionless group, function of the Reynolds number, which is the independent dimensionless group. This last problem, the pressure difference across the flow of the pipe, is also the rate of momentum transport across the surface of the pipe. The wall shear stress, force per unit area per unit time, okay, can also be interpreted as the momentum transfer rate. The wall shear stress, which is a force per unit area, can also be interpreted as the momentum transfer rate per unit area, that is momentum transferred per unit area per unit time. Okay. So, in the next lecture we will look at how to a more physical understanding of these dimensionless group, what they physically mean, what are the relations between them, and what is the reason for the form of the relations between them in the limit of high and low Reynolds number. Okay. So, this I will continue in the next lecture. I will see you there.